Example 1, area between two curves. I'm just going to draw us a little picture here. Here's my XY plane. And I got two curves ready for us. First curve looks something like this. It's written as y equals 1/2 x squared plus 5x plus 2. And I have a second curve. This is just going to be a parabola that opens up downward. Maybe it goes something like this. Boom. Boom. And we'll call that y equals negative x squared plus 3. As you look at the two curves, you see that this region right here, this lunar shape, is contained between the two curves. Because both curves are in terms of x, they're solved for y, but they're in terms of x, this tells me that I'm going to have a vertical slicing, meaning I'm going to run into that x-axis. I'm going to slice the x-axis all up. Boom, 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 boom. Just like I can create a series of rectangles through that. And from our formula, we know that we could calculate our area by saying the area should equal the integral from a to b. Now the a to b will be where these two functions, these two curves intersect. So I need this value and I need that value in terms of x's because they have to be measured on the x-axis. So here's my a and my b. I have to find those values. I'll use the calculator to find those. But then I have to set up top function minus bottom function. So in this case, the top curve is this red curve here. I'll say parenthesis negative x squared plus 3 minus parenthesis the other curve, which is the 1/2 x squared plus 5x plus 2. And all of that would get integrated with respect to x because I'm slicing against the x-axis. I'm doing a vertical slicing. Okay. Now I'm going to find these points of intersection in a second. Before I do that, I would like to simplify this expression. So I've got the area is equal to the integral. Leave myself plenty of room there. Now if I look at this, it's negative x squared minus 1/2 x. That would be negative 3/2 x squared minus 5x. See, that's why I put those parentheses there. It's so important to make sure that you're distributing that negative all the way across. And then I've got a 3 minus 2. 3 minus 2 is simply 1. Now I'm pretty much at a standstill because I have to know these boundaries. I have to know where to start, where to end. So I'm going to have to go to my calculator. Unfortunately, I already typed this into my calculator to save a little bit of time. I've got the two graphs already created. And what I need to do is find the points of intersection. How I do that? I'll hit my second calc option, and option 5 is the intersection. So I choose the first curve, second curve, put a guess in there, and that's going to give me a value of negative 3.522588. I'm going to run with this being 4 decimal places to mitigate any rounding errors in the end. And so my a value is x equal negative 3.5226 when I round appropriately. Now I can go through the same process, second calc, option 5, choose the first curve, second curve, get close to that point of intersection, and that gives me a value there of x equaling 0.1893. 1893. So I need to start at negative 3.5226 and end at 0.1893. Because these values are decimals, I know they're not very pretty, I could integrate this by hand, but there's no point because then I'm going to have to turn around and plug these values in. So I'm going to use the calculator to figure out my area. It's actually a very simple process. As I go to my calculator now, sorry for moving these papers back and forth here. I'm going to go to the y equals. I'm going to clear out both of those functions. And I'm going to type in the refined integral that I have down here. I'm going to call that -3/2 x squared minus 5x plus 1. And then I graph that. And you'll notice the picture that I had a moment ago just kind of fell to the wayside. If you're following these videos in sequence, we talked about the average value of a function and how these areas could be very fluid. They could be moved about like water and displaced and set to a state of equilibrium. If you consider this area of this loon right here, what it's doing, I'm just reorganizing it. I'm pushing all that up. It's going to be this region right here. And so to figure out what that region is, that area where my finger is pointing is the same as this area right here. I simply go to that second calc option, and this time I'm going to go down to option 7. It'll ask me, where do you want to start the lower limit? Well, I'm going to start at the -3.5226, and I hit enter, and it'll ask for the upper limit, and that was at 0.1893. When I hit enter, the calculator will shade all that region, and it'll report what that area is. The area that's being reported here is the same as the area right there. Those are equivalent areas. It's just been reshaped to fit right here above the x-axis. And this is being reported as 12 point, I'll write it here, 12.785. And I'm getting that straight from the calculator. I know it's hard to see, but that's the value that it's reporting right there. That would be units squared. And so in this example, I show how you can start with two functions. You simply find what region is being contained between those two functions. You have to find their points of intersection. Once you have those points of intersection, you can set up your integral. So I've got the area from the first point to the second point. That'd be left to right. And then this is the top function minus the bottom function that I refined. Throw it right in the calculator, and that gives me the area between those two curves. That's the area contained between those two curves. And once again, on the calculator, it may not look exactly the way you have it drawn out or the way the problem is presented to you, because you're refining that. As you refine that, those areas, what the calculator reports versus what's on your paper, those are equivalent statements. They just may look a little bit differently geometrically, because this pushes that all up and says this is the region above the x-axis. This is saying I don't really care about the x-axis, this is anywhere. So that's your first example for area between curves.